Here is something worth sitting with as you get comfortable tonight. Right now, wherever you are, particles of light are landing on your skin. Trillions of them, every second, arriving from lamps, screens, windows, and distant stars. You cannot feel them, but each one carries a small amount of energy, and each one behaves in a way that seems almost impossible. Light can spread like a wave, bend around obstacles, and create patterns of bright and dark bands. Yet it can also arrive as separate packets, one tiny impact at a time, like particles. It is not simply a wave in one experiment and a particle in another because it changes its mind. The deeper truth is that our ordinary words, wave and particle, are incomplete descriptions of something that does not fit comfortably into either category. That is the world of quantum mechanics, the theory that governs atoms, electrons, light, and the structures we know. It is one of the most successful theories ever created. Its predictions have been tested with extraordinary precision. Much of modern life, from computer chips and lasers to medical scanners and light-emitting diodes, depends on it. And yet, beneath that success, basic questions remain. What is a particle doing before we measure it? Is probability built into nature, or does it only describe our ignorance? Why can distant particles share correlations stronger than any ordinary hidden instructions seem able to produce? And why does the quantum description of matter refuse to fit neatly with Einstein's description of gravity? Quantum mechanics did not appear in a single moment. It emerged slowly through a series of practical problems that seemed unrelated at first. The color of hot metal, electrons escaping from a surface, strange lines in atomic spectra, and the stability of matter itself. Each solution opened another question, and each question pulled physics farther away from the comfortable world of everyday intuition. The story begins, unexpectedly, with ovens. In the late 19th century, physicists were studying what happens when an object is heated. A piece of iron in a forge begins dark, then glows red, orange, yellow, and finally white as its temperature rises. A carefully constructed hollow cavity behaves in a particularly clean way. Light trapped inside it reaches equilibrium with the walls, and a small opening reveals a spectrum whose shape depends mainly on temperature. Physicists called the idealized object a blackbody. The experimental measurements were excellent. The theory was not. Classical physics could describe the long wavelength part of the spectrum reasonably well, but as the calculation moved toward shorter and shorter wavelengths, especially into the ultraviolet, the predicted energy rose without limit. According to the equations, a heated cavity should pour out an infinite amount of ultraviolet radiation. Nothing in nature behaved that way. An oven does not release infinite energy. The prediction was so absurd that it became known as the ultraviolet catastrophe. Max Planck was not a natural revolutionary. He trusted the established structure of classical physics and hoped to protect it. In 1900, after years of working on the blackbody problem, he found a formula that matched the measured spectrum with remarkable accuracy. But at first, it was only a successful formula. He still needed to understand why it worked. To derive it, Planck was forced to make an assumption he found deeply uncomfortable. The microscopic oscillators in the walls of the cavity could not exchange energy in any arbitrary amount. They could emit or absorb it only in discrete portions. Energy, at that scale, behaved less like a smooth ramp and more like a staircase. On a ramp, you may stand at any height. On a staircase, only certain heights are available. Planck proposed that energy came in steps, or quanta, whose size depended on frequency. The higher the frequency, the larger the required quantum. The relationship was simple. The energy of one quantum was proportional to the frequency, with the proportionality set by a tiny number now called Planck's constant. Because Planck's constant is so small, the steps are invisible in ordinary life. A rolling ball, a swinging door, or a warm cup of tea appears to exchange energy continuously. But at atomic scales, the steps matter. At very high frequencies, the energy required for even one step becomes large, so those modes are difficult to excite. The ultraviolet catastrophe disappears. Planck did not initially believe that nature was truly quantized. He regarded the assumption as a mathematical device, an act of desperation used to force theory into agreement with experiment. He hoped that a more conventional derivation would eventually remove the need for it. That never happened. The first quantum entered physics through a problem about heat, introduced by a man who did not want a quantum revolution. But 5 years later, Albert Einstein took Planck's reluctant idea much more seriously. The puzzle Einstein considered was the photoelectric effect. When light shines on certain metals, electrons can be ejected from the surface. Classical wave theory suggested that brighter light should deliver more energy and therefore produce more energetic electrons. It also suggested that even low-frequency light should eventually free electrons if it were intense enough or allowed to shine long enough. Experiments showed something different. A faint, ultraviolet light could release electrons immediately. Making the ultraviolet light brighter increased the number of electrons, but not the energy carried by each one. Red light, meanwhile, might fail to release any electrons at all, no matter how bright it became. Einstein explained this by proposing that light itself was quantized. It arrived in separate packets, later called photons. Each photon carried an energy determined by its frequency. Ultraviolet light has a high frequency, so each ultraviolet photon carries a relatively large amount of energy. Red light has a lower frequency, so each red photon carries less. An electron in a metal needs a certain minimum amount of energy to escape. If one photon carries enough, the electron is released, and any remaining energy becomes motion. If the photon falls below the threshold, adding more photons does not necessarily help because each interaction occurs as a separate event. More low-energy photons produce more weak attempts, not one combined powerful blow. Brightness, therefore, controls mainly how many photons arrive. Frequency controls the energy of each photon. With that single idea, the strange details of the photoelectric effect made sense. Einstein's proposal was radical because light already had overwhelming evidence supporting its wave nature. Waves of light interfere, diffract, and polarize. Maxwell's equations had shown that light was an electromagnetic wave. Now Einstein was saying that the same light also arrived in particle-like packets. The contradiction was not solved by choosing one picture and discarding the other. Both were needed. Light produced wave patterns when it traveled through an apparatus, yet it was detected in localized impacts. The world was beginning to show that the familiar categories of classical physics were not fundamental categories of nature. When Einstein later received the Nobel Prize, the award emphasized his explanation of the photoelectric effect rather than relativity. The light quantum had become more than a speculative trick. It was a real feature of the physical world. At roughly the same time, physicists were discovering that atoms posed their own crisis. In 1911, Ernest Rutherford and his colleagues fired positively charged alpha particles at a thin sheet of gold. The accepted model pictured the atom as a diffuse region of positive charge, with electrons embedded inside it. Most alpha particles were expected to pass through, with only small deflections. Most did. But a few were scattered through enormous angles, and some returned almost toward the source. Rutherford compared the surprise to firing a shell at a piece of tissue paper and having it bounce back. The atom, he concluded, contained a tiny, dense, positively charged nucleus. Almost all its mass was concentrated there, while electrons occupied the much larger surrounding region. Matter was mostly empty space, but the new nuclear atom was unstable according to classical physics. An electron moving around a nucleus is an accelerating electric charge, and accelerating charges radiate energy. The electron should lose energy, spiral inward, and crash into the nucleus in a tiny fraction of a second. If classical theory were complete, stable atoms should not exist. Niels Bohr offered a strange rescue in 1913. He proposed that electrons were allowed to occupy only certain special states. While an electron remained in one of these states, it did not radiate energy. It could move from one state to another only by absorbing or emitting a photon whose energy matched the difference between the two levels. The rule was not derived from a complete deeper theory. Bohr simply imposed quantization on the atom. Yet the result was astonishingly successful for hydrogen. Hydrogen emits light at a set of sharply defined wavelengths rather than as a continuous rainbow. These spectral lines had been measured for decades, but their pattern had lacked a convincing physical explanation. In Bohr's model, each line corresponded to a jump between two allowed energy levels. The atom was not free to possess any energy whatsoever. Like Planck's oscillator, it lived on a staircase. Bohr's model explained hydrogen beautifully, but it struggled with more complicated atoms. It also left uncomfortable questions. Why were only certain states allowed? What did it mean for an electron to jump without traveling through the intermediate energies? And what exactly was an electron doing while it occupied a stable state? A partial answer came from Louis de Broglie, a French physicist who asked a wonderfully simple question. If light, once regarded as a wave, can behave like a particle, might matter, normally regarded as particles, behave like a wave? De Broglie proposed that every moving object has an associated wavelength. For ordinary objects, the wavelength is unimaginably small because Planck's constant is tiny and the object's momentum is large. A moving ball therefore shows no observable wave behavior. An electron is different. Its mass is so small that its wavelength can be comparable to the size of an atom. This idea gave Bohr's mysterious allowed states a more natural interpretation. Imagine a wave wrapped around a circular path. If the circumference contains a whole number of wavelengths, the wave meets itself in step and forms a stable standing pattern. If it does not fit, different parts interfere destructively. Only certain patterns survive. The electron's allowed states could therefore be understood not as arbitrary tracks imposed by decree, but as standing wave conditions. Quantization appeared because waves confined to a region can support only certain stable patterns, just as a string fixed at both ends can vibrate only in certain harmonics. The idea sounded daring, but experiments soon confirmed it. Electrons scattered from crystals produce diffraction patterns, a signature of wave behavior. George Paget Thomson helped demonstrate electron diffraction, while his father, J.J. Thomson, had earlier helped establish the electron as a particle. The father and son seemed to prove opposite things. In reality, both had revealed different aspects of the same quantum object. By the middle of the 1920s, physicists had a collection of successful quantum rules, but no complete quantum theory. Then, two very different formulations appeared within months of each other. Werner Heisenberg began from a severe principle. Physics should describe what can actually be observed. The imagined path of an electron inside an atom could not be seen. What experiments revealed were frequencies and intensities of light associated with transitions between atomic states. So Heisenberg built his theory directly from those observable transitions. During the summer of 1925, while staying on the island of Helgoland, he arranged physical quantities into arrays of numbers. Each entry represented a connection between one atomic state and another. He found rules for combining the arrays that reproduced known atomic behavior. There was something unusual about the multiplication. The order mattered. Multiplying one quantity by another did not always give the same result as reversing them. Position followed by momentum was not equivalent to momentum followed by position. Max Born recognized that Heisenberg's arrays were matrices, mathematical objects whose multiplication can be non-commutative. Matrix mechanics worked, but it was difficult to picture. There were no little planets circling a nucleus, and no definite trajectories hidden behind the equations. There were states, transitions, and algebraic relations. The theory seemed to offer correct predictions while refusing to provide a familiar mechanical image. Erwin Schrödinger soon developed an approach that looked completely different. Inspired by de Broglie's matter waves, he wrote an equation describing how a wave function changes through space and time. The equation resembled other wave equations physicists already knew how to solve. For the hydrogen atom, the allowed energies emerged naturally as standing wave solutions. Schrödinger's method was continuous and visual. Heisenberg's was discrete and abstract. At first, they seemed like rival theories. Then physicists showed that they were mathematically equivalent. They were different languages describing the same quantum structure. But Schrödinger's wave function created a new mystery. What exactly was waving? A water wave is a motion of water. A sound wave is a variation in pressure. An electromagnetic wave consists of changing electric and magnetic fields. Schrödinger initially hoped that the wave function might describe a real spread-out electron or a continuous cloud of charge. That interpretation did not survive. The wave function could be complex, involving mathematical quantities that could not directly represent an ordinary material density. And when an electron was detected, it appeared as a localized event, not as a faint piece of substance spread across the entire apparatus. Max Born proposed the interpretation that became standard. The wave function did not directly describe a material wave. Its magnitude, when squared, gave the probability of finding the particle in a particular place or obtaining a particular outcome. Quantum mechanics, therefore, did not generally predict one certain result for one event. It predicted a distribution of possible results. Repeat the same, carefully prepared experiment many times, and the outcomes form the pattern described by the wave function. An individual detection, however, appears at one definite point. This is seen dramatically in the double-slit experiment. Send a broad wave through two openings, and the two parts overlap, producing interference, regions where they reinforce and regions where they cancel. Classical particles fired through two slits should instead produce two simple clusters. Quantum particles produce an interference pattern even when they are sent through the apparatus one at a time. Each arrives as a single localized mark on the detector. At first, the marks look random. As thousands accumulate, bright and dark bands slowly appear. Individual events are particle-like. The statistical pattern is wave-like. It is tempting to imagine that each particle secretly chose one slit and followed an ordinary hidden path. But if the apparatus is modified to reveal which slit the particle passed through, the interference disappears. The alternatives no longer combine in the same way. The experimental arrangement determines which kinds of questions can meaningfully be answered. In the traditional Copenhagen-style account, before measurement, the system is represented by a superposition of possibilities. The wave function evolves smoothly according to Schrödinger's equation. At measurement, one outcome is obtained, and the description changes to match that result. This abrupt change is often called collapse. But what counts as a measurement? Does collapse describe a physical event or only an update in our knowledge? Where exactly is the line between a quantum system and a measuring device? The equations used in laboratory work are extraordinarily reliable, yet their interpretation remains unsettled. The difficulty becomes especially vivid in Schrödinger's famous cat thought experiment. Imagine a sealed box containing a cat and a quantum event that may or may not trigger a lethal mechanism. If the quantum event is in a superposition, applying the formalism without qualification seems to place the combined system in a superposition of a living cat and a dead cat. Schrödinger did not invent the cat because he believed ordinary cats float mysteriously between life and death. He wanted to expose the discomfort of extending microscopic superposition directly into the everyday world. Somewhere, the smooth quantum description seems to turn into one experienced outcome. The formalism predicts the probabilities with precision. It does not, by itself, tell everyone the same story about what physically happens. Heisenberg uncovered another central feature of the theory: the uncertainty principle. Position and momentum cannot both be assigned arbitrarily precise values in the same quantum state. The more sharply position is defined, the more widely momentum must be spread, and vice versa. This is not merely a complaint about imperfect instruments. It follows from the mathematical structure of quantum mechanics and from the wave nature of matter. A wave concentrated into a narrow region must be built from many different wavelengths. Different wavelengths correspond to different momenta. A nearly pure wavelength gives a well-defined momentum, but such a wave is spread broadly through space. Localization and definite momentum pull in opposite directions. Heisenberg illustrated the idea with a microscope. To locate an electron precisely, one needs light with a very short wavelength. Short wavelength means high frequency, and high frequency means energetic photons. The photon used to see the electron can disturb its motion. Gentler light causes less disturbance but has a longer wavelength and gives poorer position information. The deeper uncertainty is not created solely by that disturbance, but the image captures the problem. The quantum world does not permit every classical property to possess a simultaneously sharp value. Niels Bohr embraced this limitation as part of a broader principle of complementarity. Different experimental arrangements reveal different aspects of a quantum system. A wave description and a particle description may seem contradictory, yet both are needed, and they cannot always be applied in the same experimental context. Albert Einstein resisted the idea that probability and uncertainty were fundamental. He had helped create quantum theory, but he believed it was incomplete. The wave function, he suspected, described only our limited information. Beneath it, there should be a deeper reality in which physical properties had definite values and events followed lawful causes. His objection was not simply conservatism. Einstein wanted physics to describe a world that existed independently of observation. He could accept that we lacked information. He found it much harder to accept that nature itself offered only probabilities. The debates between Einstein and Bohr became legendary. At the Solvay conferences, Einstein repeatedly proposed thought experiments designed to expose a flaw in the uncertainty principle. Bohr would study each challenge and return with an answer. One of Einstein's strongest examples involved a box filled with radiation. A clock-controlled shutter would open briefly and allow one photon to escape. By weighing the box before and after, Einstein argued, one could determine the photon's energy. The clock would determine the exact time of emission. This seemed to violate the uncertainty relation between energy and time. Bohr was deeply troubled at first. Then he used Einstein's own theory of general relativity in the reply. To weigh the box, its position in a gravitational field must be determined. But the weighing process introduces uncertainty in that position. General relativity says that a clock's rate depends on gravitational position, so the uncertainty in height produces an uncertainty in the clock's reading. The proposed violation disappears. Einstein did not abandon his conviction. Instead, he refined it. Perhaps quantum mechanics made correct predictions while still failing to provide a complete description of reality. That question reached its sharpest form through quantum entanglement. Before returning to it, it helps to see how quickly the new theory demonstrated its power. Paul Dirac sought an equation for the electron that respected both quantum mechanics and Einstein's special relativity. Schrödinger's equation worked well for particles moving much slower than light, but a deeper description was needed for high speeds. Dirac was famous for speaking very little and choosing words with extreme care. His mathematics had the same quality: spare, precise, and guided by consistency. In 1928, he found an equation that did far more than expected. The electron's spin emerged naturally from the theory. Spin is a form of intrinsic angular momentum. Though the electron should not be imagined as a tiny classical ball literally rotating on an axis. Earlier, it had seemed like an extra property added to quantum mechanics. In Dirac's relativistic equation, it was built into the structure. The equation also produced negative energy solutions. These were difficult to interpret, but Dirac refused simply to discard them. He eventually concluded that the mathematics implied a particle with the same mass as the electron and the opposite electric charge, an anti-electron. In 1932, Carl Anderson observed tracks in a cloud chamber made by a particle with exactly those properties. The positron had been found. Antimatter, an entirely new category of physical existence, had been predicted by demanding that two successful theories fit together consistently. Quantum mechanics was no longer merely explaining old measurements. It was revealing things no one had yet seen. Wolfgang Pauli contributed another rule with enormous consequences. No two identical electrons can occupy the same quantum state. Electrons in an atom are described by a set of quantum numbers, and each complete state can hold only one electron. The first electron in an atom settles into the lowest available state. A second can share the same spatial orbital, only with the opposite spin, making the complete states different. A third must occupy a higher level. As atomic number increases, electrons fill shells and subshells in an organized pattern. This pattern explains the structure of the periodic table. Helium has a filled lowest shell and is chemically unreactive. Lithium has one electron in the next shell, farther from the nucleus and easier to remove, making lithium much more reactive. The repeating chemical behavior of the elements reflects repeating arrangements of outer electrons. The exclusion principle also helps explain why ordinary matter resists compression. When atoms are pushed together, their electrons cannot all collapse into the same lowest state. They must occupy a range of states, creating a powerful quantum resistance. Electromagnetic repulsion is part of the everyday sensation of solidity. But Pauli's rule is essential to the structure and stability of matter. On a far larger scale, the same principle produces electron degeneracy pressure, which can support white dwarf stars against gravitational collapse. A rule discovered through atomic spectra helps explain both the table beneath your hand and the remains of distant stars. During the following decades, quantum theory expanded into quantum field theory. In this deeper framework, fields are fundamental, and what we call particles are quantized excitations of those fields. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Forces can be described through the exchange of field quanta. Electromagnetic interactions involve photons. Hideki Yukawa proposed that the short range of the nuclear force could be explained by the exchange of a massive particle. The eventual discovery of the pion supported the essential insight, although an earlier particle, the muon, had first been mistaken for Yukawa's carrier. The nuclear story became more complicated, as accelerators revealed many new particles. The growing particle zoo found order when Murray Gell-Mann and George Zweig proposed quarks. Protons and neutrons were not elementary. They were combinations of smaller constituents. A proton contains two up quarks and one down quark. A neutron contains two down quarks and one up quark. Quarks interact through the strong force, described by quantum chromodynamics. The carriers are gluons. Unlike photons, gluons themselves carry the relevant kind of charge. So the strong force behaves in an unusual way. Pulling quarks apart does not simply weaken their connection. The energy grows rather like stretching a rubber band until new particle pairs are created. This confinement is why isolated quarks are not normally observed. The weak nuclear force, responsible for processes such as beta decay, is carried by the heavy W and Z bosons. Electromagnetism and the weak force were shown to be two expressions of a single electroweak framework. The Higgs field allows the W and Z particles, along with other elementary particles, to acquire mass through their interaction with it. The Higgs boson, a detectable excitation of that field, was confirmed in 2012. Together, quarks, leptons, photons, gluons, W and Z bosons, and the Higgs form the standard model of particle physics. It is astonishingly successful, yet it does not answer the interpretive questions that troubled Einstein, and it does not include a complete quantum theory of gravity. The oldest unresolved argument returned through a paper Einstein wrote with Boris Podolsky and Nathan Rosen in 1935. Consider two particles prepared in a shared quantum state and then separated. Certain properties of the pair can be strongly correlated. Measure one particle, and the result allows you to predict the corresponding result for the other, even when they are far apart. Einstein, Podolsky, and Rosen argued that if a measurement performed here can let us predict a distant property without physically disturbing the distant particle, then that property must already have been real. Quantum mechanics, which did not assign definite values in advance, must therefore be incomplete. Some hidden variables, not included in the wave function, might determine the results. Einstein disliked the alternative because it seemed to involve what he called a spooky influence at a distance. Relativity had taught that no usable signal or causal influence should travel faster than light. A complete local theory, he hoped, would preserve both definite properties and ordinary separation between distant events. For nearly 30 years, the debate appeared philosophical. Hidden variable theories and standard quantum mechanics seemed able to reproduce the same laboratory predictions. Then John Bell found a way to distinguish them. Bell asked what correlations are possible if measurement results are determined by local hidden instructions carried by the particles. Imagine a source sending one entangled photon to Alice and another to Bob. Each chooses a detector setting and records as a binary result. Later, they compare their data. If each photon carried a pre-written answer for every possible setting, and if nothing traveling faster than light could coordinate the distant choices, then the correlations would obey a mathematical limit. Bell expressed that limit as an inequality. Quantum mechanics predicted stronger correlations. The difference was measurable. A question about the nature of reality had become an experiment. The first influential tests were carried out by John Clauser and Stuart Friedman in 1972. Their entangled photons violated a Bell inequality in agreement with quantum mechanics. But early experiments contained loopholes. Perhaps the detector settings were not changed quickly enough. Perhaps too many particles went undetected. A determined defender of local hidden variables could still imagine an escape. Alain Aspect and his collaborator improved the tests in the early 1980s. In one experiment, the detector settings were switched while the photons were already traveling, making ordinary communication between the two sides unable to explain the correlation. Again, the inequality was violated. Later experiments became more rigorous. In 2015, multiple groups reported Bell tests designed to close the major locality and detection loopholes together. The results continued to reject the class of local hidden variable explanations constrained by Bell's assumptions. This conclusion needs careful wording. Bell's theorem does not prove that every imaginable hidden variable theory is impossible. Non-local hidden variable theories, such as Bohm's pilot wave model, remain logically possible, nor do the experiments allow messages to be sent faster than light. Alice cannot choose her individual outcome. It appears random. Bob's outcome also appears random. Only when their records are later compared, through ordinary communication, do the correlations become visible. Entanglement challenges local classical explanation without providing a faster-than-light telephone. The 2022 Nobel Prize in Physics honored Clauser, Aspect, and Anton Zeilinger for experiments with entangled photons and the foundations of quantum information science. What once looked like an abstract dispute had become a practical field. Entanglement can be used in quantum cryptography, where interference with a quantum system leaves detectable traces. It is central to quantum teleportation, which transfers a quantum state using entanglement plus ordinary classical communication. It is also an important resource in quantum computing, where qubits can be prepared in superpositions and entangled with one another. Quantum computing is often described carelessly as trying every answer at once. The reality is subtler. A quantum algorithm controls amplitudes so that unwanted possibilities interfere destructively while useful ones are enhanced. For certain problems, this structure may offer dramatic advantages. For many ordinary tasks, classical computers remain entirely appropriate. Even the most advanced applications do not settle what the wave function means. The Copenhagen family of interpretations treats the wave function as the complete tool for predicting measurement outcomes and emphasizes that definite classical results arise in a measurement context. Different versions disagree on exactly where or how collapse should be understood. The many worlds interpretation removes collapse. The universal wave function always evolves smoothly, and different possible outcomes become associated with effectively separate branches. From within one branch, an observer experiences one result. The theory preserves Schrödinger's equation at all scales, but asks us to accept a vast branching structure. Pilot wave theory gives particles definite positions guided by a real wave. It reproduces the predictions of ordinary, non-relativistic quantum mechanics, but is explicitly non-local. Bell's theorem rules out the local realism Einstein hoped for, not every realist picture. Decoherence explains why large systems lose visible quantum interference when they become entangled with their environments. A microscopic superposition spreads into countless uncontrolled environmental correlations, making alternative outcomes unable to interfere in practice. This helps explain why tables, cats, and measuring devices appear classical. But decoherence alone does not make every interpretive problem disappear. The combined state still contains the alternatives in the underlying mathematics. Whether one outcome collapses, branches reflects a hidden configuration, or should be understood in some other way remains debated. Physicists can agree completely on calculations and disagree about the picture of reality behind them. That is unusual, but it is not a sign that the science has failed. The experimentally tested structure is extremely clear. The disagreement concerns what kind of world that structure describes, and quantum mechanics has transformed the visible world around us. Semiconductors depend on quantum energy bands. Transistors use controlled electron behavior inside those materials, and billions of transistors form the processors in modern computers and phones. Lasers rely on stimulated emission, a quantum process in which incoming light triggers atoms to release matching photons. Light-emitting diodes produce light when electrons move between energy states in a semiconductor. Magnetic resonance imaging uses quantum properties of atomic nuclei. Atomic clocks depend on exquisitely stable quantum transitions. Even stars depend on quantum effects. In the sun, positively charged nuclei repel one another. Quantum tunneling gives them a small probability of crossing barriers they could not overcome classically, allowing nuclear fusion to proceed at the temperatures found in stellar cores. Quantum theory is not a distant curiosity confined to laboratories. It is woven into matter, chemistry, technology, and the light by which we see. Yet one force remains outside the completed quantum framework: gravity. General relativity describes gravity not as an ordinary force exchanged across space, but as the geometry of spacetime. Matter and energy curve spacetime, and objects follow paths through that curved geometry. The theory explains planetary motion, gravitational time dilation, black holes, gravitational waves, and the expansion of the universe. Quantum field theory, meanwhile, describes particles and forces as quantum excitations evolving on a space-time background. It assumes the stage is present while the fields fluctuate upon it. General relativity says the stage itself is dynamic. In most situations, the theories can be used separately. Quantum gravity is negligible when studying an atom. Quantum effects are often negligible when calculating the orbit of a planet. But in the earliest universe and deep inside black holes, matter becomes extremely dense, and both theories should matter at once. Attempts to treat gravity like the other quantum forces produce uncontrollable infinities. In quantum field calculations, temporary fluctuations appear at every scale. For electromagnetism and the nuclear forces, a procedure called renormalization allows a finite set of measured quantities to absorb the troublesome infinities. A straightforward quantum version of general relativity requires endlessly many corrections. Its predictive power breaks down at very high energies. The critical scale is associated with the Planck length, roughly 10 to the minus 35 meters. Far below anything directly accessible, it marks the region where our ordinary ideas of smooth space-time may fail. At that scale, geometry itself may fluctuate quantum mechanically. One possible description introduces a graviton, a hypothetical massless quantum of the gravitational field with spin 2. At low energies, treating gravity in terms of gravitons can work as an effective approximation. The problem is finding a complete theory that remains consistent at the smallest distances. String theory approaches the problem by replacing point particles with tiny one-dimensional strings. Different vibrational patterns appear as different particles, rather like different notes produced by one instrument. Um, Among the allowed vibrations is a massless spin-2 mode with the properties expected of a graviton. Gravity enters the theory naturally. Because a string has a small but finite extension, interactions are spread out rather than forced to occur at a perfect mathematical point. This softens some of the high-energy infinities that trouble point particle approaches. But consistency requires additional dimensions beyond the familiar 3 dimensions of space and 1 of time. In common superstring formulations, the extra spatial dimensions are imagined as tightly curled structures too small to observe directly. The analogy is a garden hose seen from far away. It looks like a one-dimensional line, but an ant nearby can also walk around its circular width. String theory has produced deep mathematical insights and useful connections to black holes and quantum field theory. It has not yet provided a unique, directly confirmed experimental prediction that establishes it as the theory of nature. The characteristic energies are enormously beyond current accelerators, and the framework permits many possible low-energy worlds, depending on how the extra dimensions are arranged. Loop quantum gravity takes a different path. Instead of beginning with strings and trying to recover space-time, it begins with general relativity and applies quantum principles directly to geometry. In this approach, areas and volumes can have discrete spectra. Space is represented through networks of quantum relationships called spin networks. The image is not of objects placed inside a continuous container. The network itself defines the geometry. At extremely small scales, space may be granular rather than infinitely divisible, as if a smooth fabric revealed a fine woven structure when viewed closely enough. Some loop quantum cosmology models replace the classical Big Bang singularity with a big bounce. A contracting universe reaches an extreme but finite density. Quantum geometry produces an effective repulsion, and expansion begins. It is a beautiful possibility, but it remains model-dependent and unconfirmed. Other approaches explore causal sets, emergent spacetime, asymptotic safety, and relationships between geometry and quantum information. None has yet achieved decisive experimental support. This leaves physics in an unusual position. Quantum mechanics and general relativity are both spectacularly successful in their own domains. We know that some deeper framework must connect them, yet the scales where the connection becomes unavoidable are difficult to test. Perhaps spacetime is quantized. Perhaps particles are vibrations of more fundamental objects. Perhaps geometry emerges from entanglement. Perhaps the language needed for the final theory has not yet been invented. That uncertainty brings us back to where the story began. Planck was trying to explain the glow of a heated cavity. He introduced energy quanta reluctantly, hoping they were temporary. Einstein treated light as packets and revealed that waves could arrive as particles. Bohr placed electrons on discrete levels. De Broglie gave matter a wavelength. Heisenberg replaced invisible paths with observable relations. Schrödinger described a wave whose meaning became probability in Born's hands. Dirac found antimatter inside an equation. Pauli explained the architecture of atoms with a prohibition. Bell transformed a philosophical argument into a measurable inequality. Again and again, the successful answer was stranger than the question that produced it. And still, the theory does not say in one universally accepted voice what reality is doing when no measurement is made. It tells us, with astonishing precision, what outcomes can occur and how their probabilities combine. It tells us that classical intuition is not the final judge of what nature is allowed to be. Perhaps understanding does not always mean reducing the world to familiar pictures. A wave and a particle are pictures borrowed from ordinary experience. Quantum objects are not obligated to fit inside them. The mathematics may be showing us a structure that our language only approaches from different sides. So as you settle deeper into the quiet, consider the light still arriving around you. Each photon belongs to the same history that began with hot ovens and impossible ultraviolet energy. Every atom in your body is held in its form by quantum rules. Every breath is a choreography of electrons, bonds, and fields. The stars burn because quantum tunneling allows nuclei to meet. You are not merely observing the quantum world from a distance, you are made from it. The unanswered questions do not erase what has been learned. They mark the edge of it. Somewhere, perhaps in a quiet office or in a calculation not yet understood, another idea may be waiting, just as Planck's quantum once waited inside. A formula he did not fully believe. There are other pieces of quantum mechanics that seem almost designed to unsettle common sense. One of them is spin. The word sounds familiar. It makes you imagine a tiny planet turning on its axis or a ball rotating through the air. But quantum spin is not ordinary spinning. An electron is not a little solid sphere whirling like a marble. Spin is an intrinsic quantum property. something particles carry in the same basic way they carry charge or mass. And yet, spin has direction. Measure it along one axis, and you get one kind of answer. Measure it along another, and you may get a different one. Some particles behave as if they need two full turns before returning to their original mathematical state. That sounds impossible if you picture the particle as a tiny object in everyday space. But in quantum theory, the mathematics is not forced to match our childhood images of objects. Spin also helps explain why matter has structure. Electrons obey the Pauli exclusion principle, which says that two identical fermions cannot occupy exactly the same quantum state. Without that rule, atoms would collapse into something far less interesting. Chemistry would not have its familiar layers. The periodic table would not have its shape. Solids would not resist compression in the same way. The firmness of the chair, the structure of your bones, the stability of atoms, and the diversity of chemistry all depend on quantum rules that are deeply unlike ordinary mechanics. Another strange idea is tunneling. In everyday life, if a ball does not have enough energy to roll over a hill, it stays on one side. In quantum mechanics, a particle described by a wave function can sometimes appear on the other side of a barrier, even if classical physics says it should not have enough energy to cross. It does not climb the hill in the ordinary sense. Its quantum state has a small but real chance of being found beyond it. This is not just a philosophical curiosity. Tunneling helps explain nuclear processes in stars. It appears in electronics. It is used in scanning tunneling microscopes that can image surfaces at atomic scales. Once again, the strange rule becomes a practical tool. Then there is decoherence, one of the ideas that helps explain why the quantum world does not usually look quantum at human scales. A small isolated system can show delicate superpositions, but when that system interacts with its environment, air molecules, photons, heat, vibrations, measuring devices, the different possibilities become entangled with countless outside details. The fragile interference between alternatives becomes effectively lost. Decoherence does not solve every interpretation problem. It does not tell everyone which philosophical story to believe. But it helps explain why a dust grain, a cat, a coffee cup, or a human body does not normally appear as a visible superposition of incompatible states. The environment is always watching, in a sense, and that constant interaction hides the delicate quantum behavior from ordinary experience. This is why quantum computers are so difficult to build. They need quantum states to remain coherent long enough to perform useful operations. But the world is noisy. Heat, vibration, stray fields, imperfect materials, and tiny uncontrolled interactions can destroy the very behavior engineers are trying to protect. The dream of quantum computing is not that it will make every problem easy. It will not simply replace ordinary computers. Its power is more specific. Certain problems involving quantum systems, factoring, optimization, or simulation may be approached in new ways. The promise is real, but so are the limits. Quantum mechanics, then, is not one mystery. It is a family of mysteries that somehow work together with extraordinary precision. Superposition, measurement, uncertainty, spin, tunneling, entanglement, decoherence, fields, particles that are not quite particles in the everyday sense. And, despite all the confusion, the theory keeps matching experiments. That is the peaceful part of the story. The human imagination struggles. The mathematics keeps working. The devices keep functioning. The atoms keep obeying rules that feel impossible until they become familiar. You do not need to solve any of that tonight. Let the arguments between waves and particles grow quiet. Let the wave functions evolve, the distant correlations wait to be compared, and the hidden geometry of space remain hidden a little longer. Let the questions drift, and let yourself rest.